welcome to our first 2026 event. Happy New Year, and we welcome Terry again. Terry, it's all yours.
Thank you, Helen. It's good to be back and I see a number of common names I've seen before in previous presentations. Good to see everybody. Okay, today I'm talking about some of the preconditions for quantizing general relativity. I'm not about to try to quantize general relativity. The topic in this one is to say that we need to take a close examination of some of the mathematics that we're using in general relativity and also in quantum mechanics. The theme is very much that the problem we're encountering is that we've hosed ourselves on some of the mathematics. We're using some mathematics that make assumptions that don't necessarily map well into the physical world, especially when we get to areas about infinities. So infinities, of course, have been an issue in mathematics since the Greeks. The Greeks did not use them. They were very cautious about using infinities, and I think for good reasons. So if you look at the structures, we use mathematics that in some very literal ways prevent a fusion of quantum mechanics and general relativity. General relativity is a continuum structure that is just sort of instantaneously incompatible with quantum mechanics, if you think about it, because if you have infinite precision, you have infinite observation. And how do you put quantum mechanics in when you have infinite precision in your observation? So let's get into it. Part one. One of the things, if you've been following what I've been talking about lately, is a redefinition of special relativity. And incidentally, I am more surprised that I did this than anybody. I did not expect to go back and say, oh, we have some issues on special relativity, because that's the simplest, most straightforward, literally algebraic part of the relativity package. So you kind of go like, what do you need to do on that? As it turns out, there's quite a bit that needs to be done in special relativity. Why is that important? If you don't have the right maths for special relativity, and I am saying that point blank that we don't, that some of the math we are using is not the right math, not the right set of assumptions, then not surprisingly, everything that gets built up from that becomes very difficult to get it in order. It's not that you can't do it. You can always find a way to work around these things. But working around something is not the same thing as, getting the best way to do this. So let's take a look at some of the recent things which has come up in previous presentations about special relativity. Starting out, here's the, by the way, I'm going to ask a question. I noticed that my image does not show up on what I see on the icon. Is that the way that should be or not? So I'm not sure if that's global for everyone. So just a little insert.
We're seeing that Minkowski original coordinate transformation figure.
Yeah, there's an insert picture that is showing that's not showing what I usually see with that. So not sure what's going on with that. That's secondary. As long as the slides are showing up, that's what's important. So this is Minkowski's original transformation figure. It's from the blackboard that he had when he did his famous presentation. And he shows some well-known figures on that we've all seen in any kind of special relativity textbook. And the thing I want to emphasize in this one is this issue about coordinate transformations. When you are doing special relativity, you cannot assume that the coordinates of space and time are parallel or in sync with your definition of space and time. And the emphasis on that is they change in an odd way too. They kind of get squashed. It's almost like you take them and just kind of like squeeze them together. And why that happens is part of what I want to emphasize on. I'm going to check again. Helen, is there a way that my own image can come up on my side image here, just so I can get an idea? Here we go. Okay, working on this.
What do you need?
Yeah, it's just I'm getting an odd. I don't know why it's doing this. but let me see if I can. Okay, that's the best I can do. So you get this interesting squeezing of the dimensionality. You have non-parallel time and non-parallel space. Of course, that's the whole point of special relativity, is that you cannot assume that your definition of time or your definition of space are shared by other people. So these are lovely figures, by the way. If you go back, and these are great fun to analyze in detail. You see that classic hyperbolic curve at the top. You get these various definitions. The 1 over c is actually a unit of time as it works out with those things. So it's a lovely paper to go over and get some detail on that. If we go a little bit farther in time, this is Richard Feynman's one of his minifigures from his lectures, and it shows essentially a redrawing of Minkowski's diagram. You see that same issue where you have the definition of x and the definition of time. Sometimes they put a c in front of it, sometimes they don't. If you use the right units, you don't have to worry about the speed of light being a factor in that. You want it so that it gives these nice square coordinates, and you see the same effect here. This essentially is a direct copy, probably by intermediate sources, from Minkowski's original diagram. So you look at the x here, and you look at the time there, and how they've transformed for a moving object, going right back to what Minkowski had to say about this. Now, why does that do that, though? It turns out there's a fairly simple way to explain why transformations of space and time work in this fashion. And the easiest way to do this is something called a light clock. I actually tend to call them javelin clocks, because the idea is you focus on the 2 dimensions that are the ones that transform. You don't worry about the other ones. The x and y, or the x and z, the y and z you can kind of discard because they don't really change much. But the time and the direction of motion, which we'll call x, those you have to worry about. And by focusing on those, you get a much simpler representation of the issues that are going on with this. So you can kind of stop trying to think in 4-dimensional space, which we're not good at because we're 3-dimensional creatures. So, but 2 dimensions, that's something we can work with. And you can get a very vivid description of what happens to these length and time measurements. The nice thing about these javelin clocks or light clocks is they give you both time and distance metrics combined in a fashion that is always relativistically invariant. It shows you the relationship between space and time. And you do this just by building a device and then watching the device as it goes by. You track that, and in your time, you see these kind of relationships. Now, if the clock is just sitting still and you map it out and you keep a record of it, keep a video of it, as it's going through time, 2 things happen. You have light pulses that come out, they go to a set of mirrors on opposite directions, then bounces off those mirrors, comes back, and when you get it adjusted to the point where they come back at exactly the same time, so they're arriving simultaneously at the pulse detector, which is in the same location as the pulse emitter, it's co-located. When you have that kind of relationship between those 2, your metrics of length and time and their angle, their orientation pop out from that definition. So this is a very, very experimental definition of what Minkowski was talking about. It's something you can actually see and record, especially with modern devices, because we can record incredibly fast on some of the modern devices. So you can actually see these effects on some of the latest types of cameras. Veritasium is coming out with, they have not come out yet, with stopping time video that addresses some of these amazing things we can do these days with devices pretty much of this type. So I'd like to keep this focus. It's a simple device. You keep it in mind, and a lot of things in relativity get a lot simpler because you say, oh, well, what will the light clock do? What happens? How does it track over time? How do I see the moving perspective? How does the moving perspective see me? Here's 3 examples. In the first one, you have your velocity where you're not moving. It's the one I just showed. So you've got your mirrors over here. By the way, can people see my mouse arrow or not?
Yes, we can.
Ah, good. Excellent. Excellent. Okay, so you have mirrors here. You have, again, the co-located emitter and detector. It sends out a pulse. And incidentally, Einstein never defined speed of light without having it come back. He never did it one way. He was very cautious about that. And there's a reason why he's very cautious about that. There's some very important relationships go on with that. So here you get these nice square coordinates. Beta is just a way of expressing the speed of light in speed of light units. So it's handy. So you just say it's a number. If it's 1, it's a speed of light. 0, you're not moving. Gamma is your classic Lorentz compression factor. This other number I've added is just a little thing that captures the geometry. It's a very obvious piece of geometry, which is how far is this angle leaning when you've got something moving at speed of light. You can't go faster than the speed of light, so this will never be more than 45 degrees. But it's a handy little angle, theta sub v, to tell you how these things are moving. 2 of the speeds I've picked here are just convenient numerically. If you I love 0.6c. 0.6c comes out with better even numbers than any other velocity, because you get exactly a beta you get a Lorentz compression factor of exactly 1.25, and has some other just nice properties. So everything just comes out. You get these nice squares that subtract, and everything works. Another interesting one is 0.866c. This is where you get a gamma factor of 2. So time slows down by exactly a factor of 2. Your clocks go twice as slow. And you see how that looks. One thing I would point out in this, you might think that a speed of a gamma factor of 2 is kind of a modest gamma factor, because they go up to extremely large numbers for particle physics. And yet look how distorted this thing is. You have this huge shape here where it's stretched all the way out here. So the image that you see of that light clock in your frame, in the original frame, is much more distorted than you might expect. Another interesting little fact I'm going to point out, if you see these gray areas here, you get the gray area here, you got the gray area here, and the same one here, that is an invariant. That area does not change in any of these figures. It stays the same. Same is true for the yellow box that the trapezoid goes in here, because it's a subset of that. That also never changes. As best I can tell from the literature, that is not, surprisingly, is not recorded in the literature as an invariant of special relativity. It should be, because it's actually a very nice one and a handy mnemonic, just to let you know. But it's a curious feature of these light clocks, is they always have this invariant area thing going on with them. So it gives you a quick way of saying, like, if the rectangle is not skinny, you know it's not right. Because if you stretch it out very far, it's got to have that reduction in width that goes along with that. Now, here's where this to me is something I genuinely find a little baffling. And I just had a long discussion in some comment sections over in Sabina Hassenfelder's Patreon, that you can go on the internet and get a beautiful description by Brian Greene on how relativity, slicing of time and everything works. And yet there's a problem that is so simple. You go like, well, why don't people talk about that? The problem is this: you have these things called, you have rotations in a hyperbolic space, which are kind of strange, but they do these beautiful little transformations. So on the left side, the observer is the bluish box, and the moving group, the moving person, is the one with the pink box. Now, if you do a transformation, is have this lovely little transformation in which you make this guy square off and you kind of go into his viewpoint. And what that does is it makes the original box slant over in the other direction. Well, that kind of makes sense, because this guy's moving. So if you take from the moving person's perspective, then that guy's going backwards and should be Lorentz contracted and Lorentz time dilated in this other direction. So you say like, oh, okay, that makes sense. And this is exactly where everybody also says, well, wait a minute, how can they both see each other as time dilated? That doesn't sound quite right. So everybody immediately has this point of hesitation. Now, the point of this figure is to make a very this is why I say, why doesn't this get talked about more? It's a very simple point. This guy over here shares an inertial frame that could extend literally to other galaxies. When this fellow in pink accelerates, he does not. In fact, his clocks, his lines, his green line, his blue line extend literally no farther than the spaceship or bicycle or car or whatever it is you're doing. For cars, the difference is very small. For a spaceship, it gets enormous. But it doesn't matter. It only applies within the domains of that spaceship. Now, you can say mathematically that you can extend that out to infinity. But the moment you do that, you're making some interesting assumptions about the speed of light. You're saying, well, this guy's frame extends out to infinity, but so what? There's nobody out there listening. Nobody else is in your frame. Nobody else underwent your acceleration. Nobody else synchronized with your clocks. So the only ones they see are still the clocks of this guy over here. So the false diagram, the one that's very easy to think is true, again, I can show you any number of good descriptions of block universe time slicing that do exactly this. They just automatically assume that this guy gets to have his lines extend out to infinity. He does not, because all of this is experimentally recordable. You know, people talk about the relativity side, but you forget. You have a gas of photons that's going out through the universe. It pervades everything. You have molecules, you have atoms. All these things are recording and can be made to record in excruciating detail what's going on. This is not magic. You don't disappear from the universe when you accelerate. You're still in it. You're still embedded. So when you're embedded in that universe, this guy is going to see these lines. And those are a very different issue. Because if you track these lines, these green lines here, what actually happens is this guy watches time go by faster in the outside universe. This is an effect, an age gradient is my own name for this. It's an equation, it's part of the original equations that Einstein put down, but he never explicitly quantified the non-simultaneity equation. Again, there's interesting reasons and why he probably didn't do that. But nonetheless, you work it out. And again, these are simple algebraic equations. There's no magic involved in this. But if you don't take that into account, if you don't take the fact that the coordinates that you're going through still belong to this guy, then you're not going to get an answer that makes any sense. But if you do it this way, then this person, as long as this one is a subset of this guy's domain, this person is always going to have time dilation, always, compared to this domain. Now, what gets weird is if this guy sets up an experiment inside of his ship, then he'll see the time dilation. He'll see this out there, but he owns all the coordinates around that experiment. You see the difference? This is hierarchical. This is like a tree. So this guy, owns this big tree. This guy owns a smaller tree. So the Poincare transformations work perfectly well in here, and he will see actual time dilation. But unless you keep track of the hierarchical nature of these transformations, you're not going to get a right answer. The proper symmetry that this represents, these slanted lines, is something called relativistic Doppler symmetry. And think about it from an intuitive viewpoint. If you're in a spaceship and you accelerate, did you change the rest of the universe? Of course you did not, because the light cone is very limited. The information coming out from you is very limited. The universe doesn't care. So if you have transformations, the transformations have to be in how you interpret the universe. They can't be the universe itself. You're not changing the universe. If you try at the moment you say that, you're violating the speed of light. So don't violate the speed of light. It's a very good principle. Stay in your light cone and you won't get some of these paradoxes. So you stay in your light cone, and what happens is you say, okay, everything outside of that light cone starts doing this weird number. So if you're heading towards Andromeda, you look straight ahead, you don't see time dilation. You see it speed up. You will watch it go play back at a fast speed. And again, this is very solid. This comes up on things like relativistic jets where they have to do this. But what's surprising is people kind of like don't sit and go through the full implications of that and realize that you have to do this consistently everywhere. So simple slide, and yet for any number of physicists, what I'm saying in this slide comes over as heresy, because you're saying that the smaller unit is always the time dilated unit. And yet from a logical viewpoint, of course it is, because the smaller unit has not affected the rest of the universe. You have to respect the location and your smallness, and the fact that the clocks that you can use have a finite resolution, they have a finite location, they're all controlled by you. Those are the ones that count. An abstract definition of time that doesn't touch matter doesn't mean anything. It literally has no meaning. You have to attach it to a clock. So what this gets into, go through this whole rigmarole, is you have a, well, actually, I'll just give the simpler part of this. This is a slide from a previous one, but I want a previous presentation. I think it was my last one. But it's very handy to recognize that the relationship between time and distance is actually a lot simpler than what you might think. You have a, think of time as being cycles. Because it is. Every definition of time you will see has a cycle in it. That's the way time works. You have a rotation of the hands, you have oscillating cycles, you have some kind of reciprocating action, which you repeat the same pattern over and over again. So if you look at this in terms of transformations done in special relativity, it gets really simple, and it does not require hyperbolic, geometries to understand what's going on. If you're sitting still, imagine this as the comparison I give is the speed movie where you can't stop. No matter what you do, you have to stop. You can go in circles or you can go in a straight line, but you can't stop. That's pretty much how time and space separation transformation works. If you're sitting in one spot, you have to go in cycles. That's time. You get pure time. You have activity. All of this is some kind of local change that's going on. If you instead decide to rev your car out and go in one straight direction at the speed of light, then you get a maximum distance in this fashion, and you go out this way. The height of these arrows always tells you how many cycles you actually encounter. So if you're down at the bottom, you encounter no cycles. If you're here, you encounter, this would be 0.866 speed of light right here, in fact. You will get half the cycles. And if you're vertical, you get all of them. So not a complicated relationship at all. And yet we tend to make it a little more complicated than possibly what we need to do, definitely than what we need to do. There we go. Going into this more detail, I've done this in previous slides and previous presentations. I'm not going to do it again, but I do want to show an example. Here again are these three examples of light clocks, which are again physically recordable phenomena. These are not abstractions. If you can do this in a lab with high-speed equipment, you can watch these light beams do these interesting little tricks and stretch out. You have your invariant area inside of the light block, which I love that invariant area. It's just a really cool little effect that lets you squeeze things and get a quick understanding of what's going to happen. I've also added a new angle here. The angle is this. Take the original block, which is always your set point for this entire domain, because this is the one that defines these brown lines, these time points that you're watching from. But take that thing and tilt it. Now, I've done a little modification to my own limits. I allowed tilting. Always before I've been tilting at the leading edge, but actually it's arbitrary either way. You can do it in the center and it works a lot better for these light clocks. So you tilt that thing and what does that do? It gives you very rapid calculations of all of the relativistic transformations by doing what? By tilting a block. So if you can tilt a block and get all of the transformations of special relativity, do you really need to make it a lot more complicated? And my suggestion is no, don't do that. If you want to see the Lorentz compression, you simply take a shadow projection going up of how this block tilts, and there's your Lorentz compression. It also shows you the position where it's going to be at. It also shows you by looking at the time signatures here and here, it will tell you what the clock's times will be here and here, because they will not be simultaneous. As you're looking at this, and you can look at it in gruesome detail, you will see that the lagging clock has a different time, has a later time than the leading clock. This is something that always happens in special relativity. But again, often is overlooked because people want to flip into the perspective of the moving object. You don't want to do that. You want to say, I don't care how it looks inside the object. I want to know how it looks to me as I'm observing it in detail as it goes through my laboratory, which you can always do. A relativistic train is still on a track. It does not disappear. That track is there. It's touching that track, and whatever the clocks read inside that train have to reconcile with the fact that it's also riding in that track. So this is, again, where I think we get a little too relativistic and forget that you can't just ignore the embedding frame. The embedding frame has all this information, has all this structure, has all these other things that are already synchronized with that set of clocks. And all of those can be used to measure and project back and forth. And when you do that, again, this guy has a very small domain, it's hierarchical, and this guy has a huge domain over here. So this guy always wins in this situation. Why? Because he's in parallel with all these lines. The other thing I want to point out in this, and again, this is from previous presentations, this is best modeled as a state machine. It is not modeled as abstract definitions of space and time. The instant you say, I have a continuum definition of time, I have a continuum definition of length, you have violated the actual physics of what we see in the laboratory. Why? Because you cannot measure a time shorter than a cycle that you have. You can extend it. You can say, well, if I had atoms that were infinitely small and were infinitely fast, then I could do that. There's nothing wrong with that as saying it's a mathematical extension. But the moment you do that and you don't recognize that there are physical limits that we have defined by things like atoms and particles and quantum effects, then you wind up having mathematics that go beyond what is physically accessible and physically meaningful in some cases. So you want to take a kind of a more strict view and say, well, based on these sets of clocks and rulers I have, what can I observe? When you do that, space and time get weaker. They become secondary characteristics. Now that sounds heretical. So how can you make space and time secondary? Well, actually, it's pretty easy. Any of you who have ever worked with state machines know that state machines are marvelous little devices. Every computer we have is essentially a state machine. So state machines, you have rules, you do transformations, you have a finite, it's important, amount of memory, not an infinite, finite amount of memory. You do these transformations, and lo and behold, you come up with a new definition. Space and time. Now notice you have change there, but you don't have to have the same definitions of space and time that we think of as just standing on their own. You actually construct space and time in that case. You actually make instances of space and time. So this guy over here, who's moving at 0.866 c, he has constructed by the nature, or someone has constructed by the nature of the acceleration and literally the structure of the spaceship. The entire spaceship has been moved at this accelerated velocity. It has created its own definition of time. It has created its own definition of length, and it's not the same as anybody else's. And when you say that, you say, oh, so space and time aren't quite as sacrosanct as I thought they were. They're actually instance-based. They're actually attached. How's that for a heresy? They're actually attached to the matter in which you have that definition. Now, this still gives you a fully coherent mathematical framework for analyzing this stuff. State machines are most definitely analyzable. They have well-defined properties. This is a state machine that has some unique properties. Don't get me wrong on that, because this is a state machine where we don't understand how it defines issues like length. We don't understand that well. That's where some of the deeper physics is going to come out, and also overall issues like quantizing gravity have to deal with this issue of how does this state machine work? What is this thing up to? And until we kind of face that and stop making space and time like overly sacred as saying that change and separation are not the same thing as space and time. Space and time are very specific instances with sets of properties defined by diagrams like this of how the transformations must work. And they are the greatest gift of physics to our universe, because without these implementations, these classical definitions of space and time, we wouldn't have information. Without information, you don't have history. All this is all tied together. It's a very interesting little neat little package. Okay, now here's where I do like a total switch on this, and this is where I'm dropping back to some older slides. But I've had these things sitting around for, oh my gosh, years, and I've never presented it. And one of the reasons why I did this one is I wanted to at least present what some of the stuff I came up with some time ago, which got some interest at that time, but I've never done a video presentation on. So that's where I'm getting into this. And the first thing I'm doing is Roger Penrose, marvelous mind, has this thing, which I don't always agree with on some points, has this thing called a conformal cyclic cosmology, which fortunately he tends to abbreviate as CCC, but then I can never remember when I see CCC. I know that's his cosmology, but I can't remember what it is. The key idea on Penrose's conformal cyclic cosmology is this. If the right things happen and the right features of matter kind of dissipate or expand, or in some way they just kind of get too unstructured just by entropy, then eventually you lose the concept of scale. And it's kind of an interesting point. You just lose the concept of scale, and the whole thing becomes small or big or whatever you want all over again. So this is how he does a cyclic cosmology. He doesn't try to shrink the universe back and expand or shrink it like some strategies. He simply says that if the universe expands in certain ways, that eventually it just erases its concept of scale. I remember I was just saying length and time are arbitrary scales that you build inside of a state machine. This is a little bit like that, but it's on a much larger scale. He's saying that you just sort of get so unstructured that it erases. Sabine Hassenfelder doesn't like that because she says protons don't do that. I agree with Sabine Hassenfelder on that. I don't see any scenario by which a proton suddenly loses its definition of scale. And as long as you've got a single proton in this giant cosmos of expanding size, you still have a scale metric. So I think Dr. Hassenfelder makes a very good point when she talks about how that's hard to do. You can't do it by just dissipation. So this led me, though, to looking at something else I had already been involved with and saying, well, are there some alternatives? And actually, I think there are. And the alternative, this kind of covers it right here, is a dual universe concept. And the central idea of this dual universe concept is that when we talk about antimatter as being matter that is going backwards in time, which is a very common theme. You see that especially, Richard Feynman got his Nobel Prize literally for exploring that concept, that antimatter was a positron, was an electron going backwards in time. It has some beautiful text about where he did that. So this is not a new concept. However, the trouble is that antimatter has positive energy. It does not have negative energy. That's been confirmed to me. It has positive gravitational mass. It does not fly away from the Earth. They've been able to do enough work, I believe, fairly recently with some atoms of antimatter, which is a very tricky experiment, but to show that, yeah, antimatter has mass. It has a positive mass. So this is similar to the dual universes that Sean Carroll, for instance, came up with back in 2007. However, this little puppy down here is not antimatter. This is something that has true negative mass. That means if you put them together, you don't get a bang. If you put matter and antimatter together, you get a bang. If you put contramatter and regular matter together, you get a big foof. They just disappear. So what does this have to do with Penrose's idea? Well, the idea is pretty simple. Instead of waiting for protons just to somehow dissipate kind of magically, this says that we're actually kind of a gigantic virtual particle experiment, one that has lost its way and keeps expanding instead of coming back together. So the idea that you could have two universes that are not that different from two virtual particles, except that they're much more durable. They last, but not forever. So the idea is that some of the expansion, the accelerated expansion that we see, is actually showing us a little bit of structure from this universe, from this pairing of universes. We're curving because we're trying to do the big fade, and we're trying to get back to that state that Roger Penrose wanted, where you start all over again. But you do it in a much more amusingly, and instead of the final crunch, you just have this final like poof, everything kind of disappears. Then you're back to Roger Penrose's CCC idea, but only by adding quite a bit of turf with this. If you do that, you take this standard model we have this rapid expansion, and then this accelerating curvature that's going on, but you have two of them. You have one going up, you have one going down. It would be contrary to our definition of time, but again, time and space are mutable state machine type characteristics. So causality is, causality is going forward in both. So it's not really correct to say it's going backwards in time. Geometric time, definitional time, directional time, you can make different versions of that. But that is a different way of doing it. Turek and Boyle are the strongest ones on dual universe these days, and I love some of Boyle's some of their papers. I also disagree on some of the details in the papers, but I think they have explored it and made mathematical predictions that no one else has gotten close to. The original Sean Carroll model from much farther back, from 2003, I think I said that date wrong. 2007 is when I first started exploring this, but 2003 was using conventional antimatter, so you have problems with that. Whereas Boyle and Turek are doing something much more exotic. So I'm not the only one talking about dual universes, but I do have a different twist on it. There's an interesting thing, and I went in more detail back in the original slides with this. If you take this idea seriously, how do I put this? The end is nearer than we think, because the expanding acceleration rate, the increasing acceleration rate of the universe, which people have talked about for decades now, is an indication that the loop back process is actually farther along than we realize, so that we're kind of topping out here. And although we won't see it that way, we would start curving back and go to the big poof. So according to this, rather than having a universe that's going to last for, trillions of years, no, this is a universe that's saying like, yeah, it's time to get back together here and try this again. So an interesting thing, you can actually measure that. You can make a definition of this theta rate, this angle of change rate, by looking at the expanding acceleration rate of the universe. So I just find that amusing, the idea that we may be nearer the end than we think, and the end will be pretty unspectacular in some ways, but interesting in other ways. And here's where you get into more detailed calculations, where you can go out and figure out what the metrics are for a cycle. And again, I find it fascinating that just based on our standard figures, you can see for the increasing acceleration rate of the universe, that we may be pretty far along in this cycle. Now, oh yeah, and here's this is just showing just that. So you start out, if you think of it as a donut, that's not too bad, and you think of the universe as being a circular donut. Are we talking about higher dimensional spaces? Yes, we are. So yeah, you got to be careful. What the donut in one thing looks like something else, and these higher dimensional spaces are really great fun to explore sometimes. And I always like to tell people there's two kinds of holes in four-dimensional space, and they both exist in three-dimensional space. One is a ping pong ball with a hollow interior, and the other one is a conventional donut. And you have to look carefully to realize that four-dimensional space has two kinds of holes. Five-dimensional space has three kinds of holes. This is not a complicated process. But the fact that both of those holes exist in three-dimensional space because you pulled out a dimension to create the hole, which is that little gap in the middle, is kind of intriguing. And a donut in four-dimensional space, a plane can go through it. Try to do that in three-dimensional space. It doesn't work real well. So here we have these higher dimensional spaces. You just got to start a cycle. That's your Big Bang, but it's got two universes. They expand outwards. You get the acceleration. There's present error. At some point, you reach an inflection. You start coming back this way, and they annihilate. Now, there's been all sorts of interesting, and here's the conformal rescaling. Once you get rid of those darn fermions, then you really do have no scale. And you have the possibilities that Roger Penrose has talked about in considerable detail and also gotten some interesting experimental data that seems to confirm there could be echoes from a previous cycle. I think that is absolutely fascinating data. But this would give a mechanism for doing that, is it allows you to get rid of those darned ornery fermions and go back and have a true reset, but not without some carryover. That's the other cool thing, is you get some carryover between these universes. So intriguing set of possibilities with that. So get your expansion, your cycle, it goes bigger. Why is this thing getting bigger? Because we have this curious thing called time. And if you think of virtual particles, you have a positron, electron, they go out this way, they go and come back together because there's nothing to keep them from doing this. Say, hey, wait a minute, you got a positive charge, I got a negative charge, let's get back together. They go back together. Time is the wrench in the mechanics. And part of the time, the reason why I have time is a little thing called hydrogen atoms. You don't think of hydrogen atoms as being fundamental, but trust me, if we didn't have them, we'd just go back and go, we'd gone again, because it'd be positrons, electrons, they'd go back together, and that would be the end of it. We have something called protons. Protons are related in an indirect way to electrons. It's not a coincidence. They have exactly the same charge, but they can't cancel. So when they try to get back together, they go, what? Whoa, what? You got quarks. Where'd you get the quarks? What are those? And they say, you're electron. Where's your mass? I can't cancel. You don't have enough mass. So they just sit there and stare at each other for eternity in a little thing, a little mutually observing circle called a proton, called an atom. And that atom is able to just expand in a fashion and separate in a fashion that wouldn't be possible if you didn't have this almost erasure of those forces. So this is what's going on with the fact that we have hydrogen atoms, that we have these off-balance cancellations that don't quite cancel, enables this definition of time. It enables this idea that things can persist. And once you have that persistence, they can expand and get bigger. This is where you have the interesting parts of how space expands and how it expands into a bigger and bigger universe, eventually with some kind of a termination at the end. But still, you can have some very interesting opportunities for things like us in the intermediate steps. You can represent this in a more, actually, I think this is kind of I don't think it's just a fun representation. I truly do think this is part of what's going on here. There is a field that we don't understand and we don't see well, and it's a dipole field that essentially is time itself. So definitions, if you want to get into the concept of how we do quantization gravity, if this is what's going on, you are not going to quantize gravity without some kind of deeper understanding of this kind of a structure. If there's a field, I think my aeroboic field, which is from Roger Penrose, it uses the term aeroboic, I believe is somewhere I got the phrase from some of his work. But this is the field that says, you know what? Yeah, just like the positron electron. I think we need to get back together. We can't do this forever. The trouble is those darn non-cancellations make it really hard to do that. So they have to go these big convoluted routes to go out and try to make those things happen. So time is a dipole field. It suggests that there's a field that we see traces of it with the Higgs interaction, but we don't have a good solid understanding of that. This comes up into be 7 + 1 is the dimensionality. Again, some of this is from years ago. I'm sure I would, at some point, I'd like to re-examine this and say if I still come out with the same eightfold shape with that. The relationship to hypercomplex numbers is not accidental. Hypercomplex numbers have got to have a part in this. There's too many things where they just match up in the structure of a universe for there not to be a relationship to the hypercomplex numbers. I think that the 7 + 1 is the octonions. You got the quaternions. You keep doubling the number of dimensions. So there's an interesting thing going on with this. Now, part of that same Okay, and again, my apologies for covering. I'm just jumping. I'm having fun with it, but I'm just jumping in some totally different topics in this. Most of our interpretation of physics has this curious characteristic that we assume everything is there. It just we take the infinity, we go to the max, we have an infinite number of infinitely tiny, infinite this and infinite that's. You put them all together, and somehow they mostly cancel out. Okay, I just want to point this out, and this is the algorithmic part of me coming through. Is if you're doing that, you almost certainly don't have the simplest mathematical structure. I mean, come on, because first of all, the infinities don't exist. You can't have an infinitely small electron. So why are you building your wave functions around the concept that an infinitely small point-like electron exists? Because if you can't observe it in the physical universe, you want to be very careful that I know there's a lot of people who really like to have a point-like particle, but I would at least ask you consider the idea that because we are classical creatures, that is literally hardwired into our brains, we want things to be small little objects. And we have a universe that gives us an amazing ability to get extremely small little objects. So of course we tend to feel that's right. But if you want to get to the deeper infrastructure, you need to pull back from that a little bit and say, well, maybe it's not quite that simple. Now, what does that have to do with this slide? Many of our interpretations of forces are that if you just put enough energy together, you bang them together hard enough, they all suddenly become a single force and everything gets unified. I want to suggest a much gentler interpretation, which is in cases where you don't see a difference, there is no difference. That is, the actual context is what's driving the differences between those. So if you look at particles, certain particles where they have a charge is a mixture of color forces and of electric charges that hold together pions, the internals of pions, you got a couple quarks that are circling around each other. The standard way to do it is say it's an infinite mess of an infinite number of thises, that's, and all working together furiously. And yeah, but you don't have to do that, because if there are no overt symptoms of anything going on under normal circumstances, default to the simplicity of saying that's because there is none. The forces don't separate at that point because they're not separated. The electric force, the color charges are all the same force in those particles, such as the pions, internally. When we interact them with other things, then we get all sorts of complexity. But you don't want to put the complexity first. You want the complexity to be emergent. This goes also back to the theme I said earlier. Finite information state machine. You don't have infinite information. So when you're trying to represent a pion, you don't represent it as an infinite number of complex particles all popping in and out of existence. You use the state machine to say, okay, it's got the minimum characteristics that can turn into electric charge, blue, red, green color charge, if you put them into the right circumstances. You have a proton, it's stable. You can say that it's an infinite complex entity of gluons and quarks and everything, or you can say it's a stable state in which those distinctions really are only implicit. And when you bang it with enough energy, then you come out with those different things. You wind up with the same algorithms, but the interpretation is very different. And it's also a much milder interpretation. A sparse information interpretation says you generate things. You don't have them all the time. You have them when you make them, but you have the recipes there. You have a proton. The proton has recipes for doing all sorts of marvelous things, and the recipes are hardwired into it, and they're very intransigent, but they don't actually express themselves until you get up to another charge. So this is talking about, there's an old idea of what they call prions, which are supposed to be smaller particles that you can do that. Prions are best modeled as coordinates. They really are. If you try to make prions into particles, it just creates all sorts of interesting quirks and incomplete definitions. Whereas if you just define them as three orthogonal dimensions, everything works out very nicely, and you wind up getting much closer to the regular physics. So the idea is that these things are different directions. So different way of looking at some of the same math. Why is it important for quantizing gravity? Because, once again, if the default structure of the universe is a minimal information state machine, then you have to look at things a little bit differently. You have to say, like, what are these very simple states that have complexity of expression if you bang them with enough energy? And this is one example of that. Now, here's the pion versus. I was talking about the pion. It's exactly what I was just talking about. Is yes, you can say that a pion is a quark and an antiquark with an incredible variety of things. The math gets really interesting in this, by the way. And the math calculates correct results. This is an important thing. I'm talking about algorithms. Algorithms, in an algorithm, you always say, like, just because you can calculate it that way doesn't mean it's the best way to do it. And that's exactly what I'm saying here. I'm saying, yes, we need these things to express the behaviors, but if we try to make them into real particles, we're almost certainly not using the most efficient algorithm. So then if you go down and break this up more into that prion type of concept, you get a much simpler definition. You get these different forces here. And you can go even farther, in which you just have a single force particle, and it's not a unit. You don't have to unify. You don't have to make a gigantic particle collector to do it. It's just there all the time. And the expression of it is what we get when we start banging it with higher energy. So it's a very different take on how unification of particles comes around. Little side note, I can't resist this. Hilbert spaces. Hilbert spaces are essentially a generalization. That's oversimplifying, but a generalization of three-dimensional space with your dot products, with your ability to do all these neat operations that are fundamental to large language models. By the way, the whole transformer model is built around the same concept. They're essentially a giant Hilbert space. So you got these giant Hilbert space with all sorts of dimensions. In a case of a large language model, the dimensions represent different concepts. And you have this very literal high-dimensional space of concepts. And then you kind of navigate through that and do dot products, and you get all sorts of just fascinatingly plausible results from doing that. Although you have to be a little careful about how you get to that. Now, what I'm going to make a point out here, though, is we talk about Hilbert spaces, and it's always, I think it's always dangerous to say, just because I have a mathematical abstraction, that the abstraction is the hammer I must use for everything. In the case of Hilbert space, the more dimensions you add, the darker the space gets. It's not the only problem with Hilbert space, but the more dimensions, the darker it gets. In terms of dynamics, if you're saying, I want to have, for instance, quantum states moving in a Hilbert space, you need to be careful, because if you really, really, truly have Hilbert space, you absolutely, it's the real thing. You can't move. You can't change state. You can't go out to some other place because everything's dark. You're hosed. There's no direction you can go that takes you anywhere, because everything dissipates instantly when you try to move. So, and there's others, again, Sabine Hossenfelder recently showed some other problems with higher spaces. Your orbits collapse if you go above three-dimensional space. I did not know that. That was a new one on me. That's fascinating. But you can't really do dynamics in Hilbert space. And yet we use them as what we think are the fundamentals of quantum mechanics. The suggestion is, as usual, as I said in the previous example, what we really do is much more constrained, but we just kind of keep pretending that we're doing something else. One example I gave is if you semi-randomly cross the entire country using map and go back in that, you feel like you've seen the entire country. You feel like, oh yeah, everywhere I go, there's something there that I expected, so everything must be there. But the reality is you haven't. You've only created that one path. You've only created that one direction. And this is kind of what happens with quantum mechanics, is we have all sorts of things where we're really bringing in classical certainty that then constrains it. So we only have a few dimensions in front of us that open up to us. And I think the more we get into this idea of contextual navigation of these spaces, I think we get a lot better in that. Another way of saying this is the infinite Hilbert space. That's your multiverse. That's your infinitely expanding wave functions with no constraints whatsoever. Well, the trouble is, if you have no constraints whatsoever, you very quickly code infinite information on a finite wave made out of a finite mass. And you just can't do that. You just can't do that because we don't see that anywhere in physics under any circumstances. And just from a logic viewpoint, it makes sense that that's hard to do. So let's be a little careful. Mathematical abstractions are powerful when we connect them properly, but we need to be a little cautious about the infinite limits. Getting back to the dual universe, here I'll just drop this one on quickly here. I'm suggesting that these two universes are dominated by what we think of as fermions that respond to the weak force. My apologies if you don't know any if you're not a particle physicist, just kind of bear with me and I'll go through it. There's a thing called a weak force, and every particle that you think is one particle is not. It's two. For instance, you have a left-handed electron and you have a right-handed electron. And these two guys kind of get together in a fashion that is surprisingly ill-defined. If you actually look, if you look at the details of literature, is it a superposition? Is it an interaction? Yeah, you get different answers depending on which part you read. So, but there are two of them. There are definitely two of them. And you can see them experimentally. And one of them responds to what's called a weak force. This is what makes nuclear reactions possible. The other variety is completely blind to it. It doesn't see it. It says, weak force? I don't see any weak force. Don't know what you're talking about. And the fact that these two are then together form what we think of as the massive electron, the electron with mass. Notice how mass is popping up here all of a sudden. So you get these two together, and then they become the particles that we think of. Now, if you think back to that figure I showed earlier about two universes, this is saying that there's a connection here between these ideas of weak blind particles and weak aware particles. And you can find both sets of particles in both universes, but the idea is that one or the other dominates in that particular universe. So that aeroboic field I mentioned earlier, it forces a certain set of dominances between one type or another type. It's not that you can't find both particles. You have to find both particles. That's how you get mass. However, if you think of it in terms of having a slight dominance of the weak aware particles in our universe and a slight dominance of the weak blind particles in the other universe, you get a very different kind of a structure with that. Neutrino is a really interesting example in this because neutrino, we only see one kind of neutrino. We think, kind of, sort of. There's debates about that because there does seem to be some kind of transformability, some kind of a mass that's associated that implies that we do have this other type of neutrino in our universe. But the resolution in this and the dual universe thing is simply that because these two neutrinos have no charge, they don't bind to each other, so the two types just fly off in different directions, and only one of them is allowed in our universe in large amounts. The other amounts would be vanishingly small. And then the other universe, it would be the reverse. You find these neutrinos would be the dominant neutrinos in that universe. So that's this is where I tend to disagree a bit with some of the work by Boyle, where they kind of, I'm not sure if I disagree with it or not. I just think I think they're emphasizing maybe too heavily the idea of these other neutrinos being very massive, but there may be an interpretation where that works. But an interesting thing. So the idea is that the reason we don't see those neutrinos is because they can't bind with their partner, and when they fly off, the field that defines the two universes just doesn't let them hang around very long. Space and time as emergent properties. Okay, this is following up on what I was just saying about these two types of electrons. We're familiar with, if you've heard any particle physics, you've heard the idea about virtual particle pairs. This is usually presented in terms of probability mathematics. There is a math issue in this because I would say that simply following that train of smaller size means higher probability. You quickly get into the affinities issue. You get into that's where you get the infinite mass of the vacuum. You get infinite, all sorts of stuff become problems. The quantum field theory that works beautifully everywhere else becomes an absolute disaster when you try to follow that route. That's a hint. It's saying we probably shouldn't be doing quite that route. So you get these virtual particle pairs that the conventional description of them. They go, they separate for a little bit. They come from nothing. They hang around for a little bit in time, and they go back together. So there's another thing you can do with that. Oops, maybe I get this a little bit out of order. This is the idea I was saying earlier well, okay, I am a little bit out of order, so let me look at my own slide for a second. This is talking about the distinction between matter and antimatter. And because in matter, you have one set of particles respond to the weak force, and antimatter, you have the other set of particles. So you have right-handed time pairs, left-handed time pairs. I think I meant to leave this slide out, so I'm going to skip right over it. And what I want to emphasize, oh, okay, so maybe that was a prelude to this line. There's another version of the annihilation reaction, because you have chirality in these pairs. You have different kinds of chiralities. You have different kinds of particle pair creations. And another one is to do a time pair creation. The other one was a space pair where they separate in space. You can also separate in time. And that starts getting interesting, because when you can separate these particles in time based on the chirality, you wind up having a structure in which time becomes a destabilized version of these time pairs. As you have these things popping apart, they form a little brief definition of time. But then if you have a slight excess of one type of the particle, which would be the weak aware particles on our side, that hoses that separation and actually breaks it and causes it essentially to move forward. So you get this whole process wrapped together. You wind up with a particle level definition of time in which this thing is kind of shooting forward in time, oscillating between these different states. And then you have this persistence that we think of as an enduring particle. So to do this, though, you have to have these left and right-handed pairs. You can't do this with just one. And also, you have to have true negative mass on these particles. You can't just have a pretend like we do in antimatter. These have to have an actual negative mass, or otherwise the cancellation doesn't work out. You work this all through, what you wind up with is the universe we live in is one in which we're dominated by a slight excess of the weak aware particles. Doesn't mean the other particles aren't there. It just means they're all involved in this little dance down here where they're constantly being annihilated. This is your relationship between the left and right versions, is they're popping in, they're destroying each other, but the net result is they move forward in this aerobaric field. This is where you get an equivalence also what we call the Higgs field. I call this an aeroboic field when I'm talking about it from the 8-dimensional viewpoint, from the 7+1 viewpoint. But if you look within our own local viewpoint, there's an equivalence here. And part of what happens is this same particle that was going backwards in time, the left-handed positron, looks like a right-handed positron going forward in time. It looks like an electron. So you have two different ways of looking at the same dynamic. And from our perspective, we see this and we call it a Higgs field. If you look at it from that broader perspective, you have this, to me, much more interesting relationship where these things are popping on and annihilating each other, exactly as Feynman originally proposed on his paper that he got the Nobel Prize for, except in this case, it turns out the negative mass was real, whereas in his case, it was a positive mass. So that's the difference. He had the same idea that was going backwards in time, but he used a positive mass version of this, whereas this one is a true negative mass. It gives you a much cleaner representation when you go this round. Jumping topics again, my apologies. I'm just a number of things I've had from sitting around for a long time, and I want to get those. You've heard of the idea of a universal wave function, and I would strongly encourage, based on the same thing as I was saying earlier about special relativity, that the speed of light really is a constraint, and it's a constraint also on wave functions. So you can create a wave function, a quantum wave function, but you always create them classically. That's all we ever see. If you get a nice little electron resonance going on inside a ring, you have to set it up classically. You don't just get it from some previous thing. And that goes back to that issue about the Hilbert space. The Hilbert space is infinitely dark unless you acknowledge that you're actually setting up much smaller wave functions that are much more constrained, much more local. You can keep saying this local theme keeps popping up, and for good reason, because both at the quantum and special relativity, you need to take the locality into context. So the idea is that the waves that we get on these quantum effects are bound by the light cone, and that's very important to recognize that. So people like to dwell on the instantaneous nature of seemingly instantaneous. It's more complicated than that, of entanglement. What they forget about is that you don't get entanglement until you spread at the speed of light in the light cone. So for instance, if you're trying to do entangled bits in quantum cryptography, you have to wait until you've had a speed of light delay to get the entangled bits to the other parties. It's not instantaneous. The entanglement part, after you've done that, that part doesn't match well with our usual conceptions of space and time. But the spreading matches very well with our usual definitions of space and time. Again, constrain the Hilbert function. Acknowledge the fact that we have a universe where we have finite causality, we have locality, we have finite information, we have minimal complexity, we have a maximum complexity for a given set of mass and energy. You've got to encode what you do with what you can. And beyond that, you only have potentials. So very different from saying there's an infinite number of things out there. You have infinite potentials, but then you got to navigate using this more local type of effect. In the mathematics, and again, this is one that I've looked at more in the past, but I was kind of amused by it when I went into great detail. It's very common in a lot of mathematical descriptions of quantum phenomena to do functions that you just sort of piece them together. So when if you got a spot right here where you take one wave function and then you graft it into another wave function, and you wind up with this nicely smooth thing. What I'm saying is that smoothness, did I just do that? What did I just do? Oh, that was weird. So this smoothness is bogus. If you if you look at it detail and you break it down and say, what point does it exactly become completely smooth? You find that you actually have an infinite series of getting smaller and smaller, and the smoothness is really kind of bogus. And yet smoothness is like the mantra that everybody wants for doing these kinds of mathematics. Well, the overall point I would get at with this is, don't make smoothness, infinite smoothness, the foundation of physics. If you do that, you are going to have a mess. It's just, we do have a mess, because if we assume that infinite smoothness and the ability to do any number of differentials in something is a definition of what makes a universe, and in fact, the universe is a state machine with finite information density, I guarantee you, no matter what you do, it's not going to work right, because you're assuming a level of smoothness that cannot exist. It's not just a matter of whether it exists, it just cannot exist. And the other thing you point out is, this is a faith kind of assumption. It's one of those things where you just kind of take it on faith. You heard that infinite smoothness and differentiability has to be the foundation of the universe. Really? Because we don't really see that. It's an interesting assumption. It's an interesting premise. But I think also it's a premise that we want to be very careful about, because we don't really see that in any kind of actual experimentation. And they say, well, yeah, but I'm going the ideal. But yeah, if your ideal doesn't map correctly into the physics that you do see, you might want to look at that a little more closely. And the natural, okay, and this is same thing, when just like the alien in the bicycle who suddenly takes off and creates his own inertial frame, for closely related reasons, because there's a relationship between acceleration and observation. For closely related reasons, your wave functions are also nicely bound by whatever the light cone is. So you can't really get beyond that. This idea of a speed of light barriers is really handy. We should use it more often. Some guy a century ago came up with it. I don't know. But it amazes me sometimes how often often accidentally by way of math, we trip ourselves up and go into infinite velocity wave functions or infinite velocity space or infinite impacts. So in an example I gave earlier is, it doesn't matter how much you accelerate locally, you're not affecting the rest of the universe. You're just not. There's a light cone around you, and that light cone, the rest of the universe doesn't see you, it doesn't care. Same thing for the quantum wave functions. It doesn't see you, it doesn't care. Respect the speed of light. Realize that these phenomena take some time. By the way, if you put that analysis onto Everett's thesis, oh wow, that looks awful. That looks awful because that thesis violates speed of light constraints in so many ways, so quickly, mostly through the Hilbert function, that it's not funny. It doesn't respect the idea that dimensionality has a relationship with wave functions. We have this duality, the Fourier duality. It doesn't respect any of that. I have seen at least one note that said that one of the reasons why Everett abandoned all of the physics and wouldn't even talk, he didn't even tell his own children about his theory. His kids were surprised when they found out how famous his theory was. But there's at least one source I saw, probably not a good one, but it suggested that it was actually kind of a prank on Hilbert's force. He was just kind of yanking people's chains. This has happened in academia before. And then when it got taken so seriously, he just bailed out completely. He certainly did not seem to be particularly proud of his own theory. He did not talk about it. He did not address it. He didn't go to meetings about it. He wanted nothing to do with it. But in terms of why it could be a prank is, I read through it and go like, this is so exaggerated in terms of how it ignores basic issues of speed of light propagation that it's a little hard to swallow that he was, that unaware of some of the restrictions. So who knows? It is just interesting. But if you respect the speed of light, you can't separate universes due to one event right here. Duh, because it takes speed of light to expand. And if you're talking about actual wave separation as it works in real, like radio waves, like where we get different bands for frequencies, you also have to have a wave train. So you can't just do it once. You have to do it a whole bunch of times in order to repeat over and over again to define which universe is this one, which universe is that one. None of it makes real, coherent modeling sense. It just doesn't. Now, if you go and just talk about only as a wave, then you can get at least a somewhat more coherent version, but then you immediately violate information issues. You create waves that have infinite information on them, and that's the very thing that got us out of classical mechanics into quantum. Last couple ones in this. Can you have tunnels? Can you have wormholes? No, you just can't. So if you deal with the aerobolic field, this is long before I started hitting on the much more recent, just really last couple of months, the finite state machine interpretation of universe dynamics, emphasis on the finite information state machine. You get the same answer. It just emphasizes it more. The aerobolic field approach simply annihilates any attempt to do something like a wormhole. And yet, ironically, it also says that the negative mass constructions that you need to create wormholes not only exist, but they're in our periodic table. They're in the standard model. Half the fermions in the standard model are negative mass. So you have an irony that you get the negative mass you want, but can you create a wormhole with it? No, you can't, because it will immediately annihilate itself. So you get a simpler form in which you just get a wavefront, which is the the state machine, moving out, and eventually probably annihilating and creating another cosmic cycle with Penrose's reflections from the previous era. So good luck in getting through that event. That could be a tough one. Infinite smoothness, beware. If you have finite resolution, you got these sheets, these things where you're trying to say, you got different definitions of this. Riemann manifolds, we always like to make them infinitely smooth. If you want to get to quantizing gravity, here's a suggestion: don't do that. If you go down to a point in which the sheets are finite themselves, they have a construction of relationship to the underlying state machine, I think some of the issues on quantizing gravity should disappear, and this is something I really want to look at more closely. But I think there's a good possibility that some of these things will just turn out to be artifacts of the mathematics, and that you can quantize the gravity issue. There was a time I used to not think that. I used to think that the gravity was, because it was smooth space-time, that it would never have a quantized type representation. And I've actually flipped on that. I'm going like, well, no, if you go with a state machine type model, yeah, there should be ways in which you can get gravity so weak, for instance, that you start seeing individual little boop, snaps of the gravitational force, and those would show up as jumps. That would be quantizing gravity in a sense, not necessarily as a particle. So yeah, this gives you more options for doing it if you get away from the idea of infinitely smooth manifolds. Why is that a problem? Because infinitely smooth manifolds unavoidably imply infinite information density, because you can't have a perfectly smooth manifold unless you have every single little tiny detail defined. And we do that, and of course you can't do good quantum mechanics on that. Everything's already observed. So a final one, this is more, I like this one just because I find this extremely amusing. If you go to, and I've talked about this before in some presentations over the last year, but if you go to a Marvel movie and you see the Hulk talking, or Bruce Banner talking about, looks like an Einstein-Rosen bridge, where he's talking about this gigantic, enormous thing that's tearing the world apart. And they look back at Einstein-Rosen's original paper of what an Einstein-Rosen bridge was. The contrast is just absolutely hilarious, because he was trying to make a model for neutrinos, little bitty tiny neutrinos that didn't work very well. That's what Einstein was interested in. He wanted to make a model for neutrinos that used two sheets of space-time, and then between those you had little holes, you have little punctures between the two space-time. And his idea was simply that those were particles, that particles always turned into little, holes between these two fabrics. It was always very speculative, and it's interesting that he came up with this dual sheet model, but he certainly wasn't talking about, he was talking about two sheets that are so close together that they're indistinguishable except for these perforations of these particles. So that was it. That was the that doesn't quite look like the Marvel representation of that, to say the least. But I do want to point out this, that if you go to the idea of real negative mass on the weak, the force blind particles in our part of the aeroboic field, in our part of our universe, as opposed to the other one, you do recover an idea that looks like a chiral version of an Einstein-Rosen bridge. And unfortunately for science fiction folks, it's not that spectacular one. It's much closer to what Einstein was talking about, which is that it's a kind of a perforation where the particles appear on either side and actually implement time in doing so. So you can come up with a kind of a recovered version of this Einstein-Rosen bridge, the original real Einstein-Rosen bridge, not these bizarre. I'm sure it's some paper I haven't seen that expands it and turns it into white holes and does all that, but I like to go back to the original papers and say, what were they really trying to talk about? And boy, it was not that. That was not where Einstein was going with that. Looking deeper, we can't understand gravity until we abandon smooth manifolds. As an adamant point of making, go to a finite information state machine model, and I think you will find that some of the things that look like absolute impediments now suddenly have options, and options that allow us to do things. It allows you to drop these quantum infinities. You can't understand gravity if you have infinite information. You can't understand quantum if you have infinite information, and you have infinite information if you have infinitely precise manifolds. Yeah, of course, they don't fit together. And this is a point that I popped onto lately, looking at actually special relativity. Tensors are important because matter is all about tensions. The whole name tensor comes from the idea if you have like a membrane, you have one set of coordinates for the membrane, but then you have a stress that you can put on the membrane. So you fill up a balloon, you have tensors, you have you have vectors that show where the tension is, and then you have the actual coordinates in that. If you go to a finite state machine model of the universe, then it turns out that tensors really are about matter, and that's why they work so well, because the tensions that you have in space-time are actually structures that are implemented by matter itself, and that includes black holes. So things like black holes do still have to have matter. This version does not allow a singularity type version, but you have this matter that is creating tensions, having relationships. So I just think it's kind of an interesting idea that tensors, the reason why they work well in so many forms of gravitational mathematics, may actually go back to the fact that they really are coming from the matter itself. Now, they have relationships that you had to implement this idea of how do they do this whole space thing. That's a really intriguing issue, but it gives you a different perspective. Negative energy. I'm big on negative energy matter. The idea that there really is such a thing as forms of matter that when they interact with our form of matter, they just go poof. They don't go bang, they go poof. Antimatter goes bang. Negative antimatter, which is chiral. You have one chirality and another chirality that have opposite mass definitions. Those go poof. And we see it all the time in virtual particles. It's actually a common interaction. Oh, and this is just to throw this in, but if you've never heard of something called momentum space, it is worth looking into. Matter can exist in something called momentum space. It has directions of at 3 axes of momentum and another axis of energy. And it has this beautiful Fourier relationship to location and time. And just to point this out, the break between these two, the fact that they're almost like, but also dramatically different, I think is probably the most important symmetry break in the universe, because it's the one that allows us to exist. It's the one that allows the easy motion of space that we have in classical location space is just the opposite in momentum space. Momentum space is like tight. It just says, enormous energy just to stretch a tiny little bit, it goes back together. Whereas we have a space where, as Casimir observed, says, yeah, the Casimir force, this is Casimir definition, not all the other definition. Casimir's definition of the Casimir force is that it's the last remnant of the bonding energy between two pieces of metal or whatever that gets separated. They don't like to advertise. It doesn't sound as fancy, so people like that infinite energy nonsense. But Casimir had it right, and this is something he talked about later on in his life, where it says, even though it has that wave relationship, it is also just the separation of these things. That separation and that very weak field is important, because that is where we get this idea of space. Space becomes kind of a field concept. And once you have space as a field concept, the idea of quantization of the gravity in space and the limits on that space, the fact that gravity itself is in some way, the fact that it's a finite field, can't go on forever, and that introduces anomalies that we think of as being the gravity part, that says you can't implement the Euclidean space perfectly. It's not possible, but you can get very close. But it turns out the deviations are extremely useful to us. Special relativity needs fixing. It's not hard. Go to a state machine representation, recognize that now is real, because that's how state machines work, and that all the energy you have is all the energy you get, and all the resolution you get is that. Is this a deterministic universe? Is it a free choice universe? if you use a state machine, it gets kind of weird. It's a little hard to say which it is, because the state machine certainly has very well-defined deterministic rules, but also it has finite information boundaries. So you can't put infinite information on it. So the answer is kind of, in terms of predictability, it's neither. It has reliable rules, but you'll never be able to figure out where those rules are going to wind up taking you. So a state machine interpretation of the universe gives you a kind of a nicely different way of looking at some of those more philosophical issues, saying like, oh yeah, we can get precise in this. And also, just mention, I don't remember if I put it in the slides. Yes. If we can quantify quantum effects in terms of state machine model, at some point, I think a real possibility of defining where the uncertainty in quantum mechanics comes from becomes possible. And I think that now that would have implications, but as long as we're stuck in the continuum model, we're not going to do that. But if we have a better understanding of how the state machine works, I think at some point we'll be able to define aspects of quantum uncertainty better. In some sense, we do a little bit with things like wave focusing. That is an example of steering quantum possibilities. But we need to get a better feel for that fascinating random observation thing where the giant wave, and they really do collapse. They're real. They bounce off things. These waves are real. They're not fictional. The wave bounces off things, but sometimes it just goes to one spot. That's the thing that we've got to figure out, and that to me is just like the key mystery for understanding how these normalizations work. So gravity is the almost canceled remnant of the largest organization, spacetime, which is what we call the Big Bang. But this initial separation of the two universes. Which, and again, I'm pretty casual about that. That particle physics matches so well with the idea that there are two universes that once you get into that mode of thinking, it's hard to get out of it, because the symmetry there is just powerful. It's overwhelming, because you have this saying, oh yeah, okay, we just got different dominances of these two types forming a universe scale virtual pair with time. And final point is that space is a very weak field. Casimir separation binding, I just described that. Quantization should be possible for issues like gravity once we realize the nature of that force and fully take negative energy matter into account. And with that, I am done.
Thank you, Terry, for the presentation. And I got a question on the chat from Louis. Are the light beams in a vacuum?
This is one of the most interesting things. If you look at a light beam, one of the reasons why, by the way, am I still sharing my screen? I'm trying to unshare here. Let's see if I can get back to, is everybody still seeing my screen, or are we seeing each other now?
Yes, I can see your
still
screen.
see a picture there.
Oh, okay. Because let me see. So give me a second here. Oh, okay. So now I can at least partially see. There we go. Okay, now I can see things. The question was about, does a light beam go through a vacuum? And that goes into I think the deepest part of why we have so much trouble with the quantum field theory when we apply it to intergalactic distances. The answer is, if you're in a laboratory and you've got light waves that are interacting with any kind of matter, absolutely you have real light waves that are propagating across that and have certain properties. When we get to the cosmic scales, this is where the definition of space has to get very different from what we're doing now. Those waves have a relationship of expansion with regard to other parts of matter, but they don't evidence themselves as actual waves until they hit matter. And this is that whole emergence thing again. A photon is spreading from the other side of the universe, has the potential to become waves, has the potential to show this. But when it's actually traveling through genuinely empty space, you never see that potential evidence itself. It's only when it actually hits things. So this is a very different way of looking at the flow of time for these quantum events. Something is going on where we always have the potential for a wave type form, but the photon really does not cross space in the conventional sense at all. If it did, then it would be stuck to one path. And the photon would go only from this point to that point. And that is not what we see. Because what we see is we see the photon goes out in a large expansion. And that large expansion has real properties, including reflection, until an additional event in which the energy gets deposited, thunk. All of a sudden, all that goes out the window. And this is a deep mystery, but and I think an approach to it, in fact, is, again, I'm going to emphasize, state machine model gives us a different way of looking at that, because space is no longer as fundamental as it was. It's an important property of the state machine, but it's a constructed property. So the idea that a photon can change state without actually traveling through some different location gives a very different take on things like double slit experiment, wave collapse. You just find a much more interesting and, I think, higher potential mathematical model for where some of it is coming from. So yeah, do I believe that there are electrons going as a wave through empty space? No, because if you do that, you immediately have a fully classical universe in which photons have a well-defined direction. Every experiment's ever been done on that type of phenomena says that's not true. They don't have a well-defined direction until they're detected. And the double slit is the classic example of that. So people want to make the electron go through both slits. But what's really going on here is a more complicated relationship in which the state machine saying, here's the options here. Well, that's not going to map into ordinary space very well, and it doesn't. And the state machine doesn't care. It just says, like, okay, here's what you get. So that's a fascinating area, and of course relevant to things like quantum computing, because quantum uncertainty. I like the idea that life seems to be able to direct quantum probabilities better than we do, and we see this all the time. We just accept it as a given that biochemical molecules, which are extremely well designed, well structured little devices, they're not just random, but you put those things together and suddenly they do squirrely things with probabilities that we have no clue how they do it. Even now, and it's amazing. How do we still not understand that? And I think that has to deal with these same issues too. That there's this fascinating infrastructure that's deeper. It evinces itself as non-spatial relationships, and it forces us to think that you can have an electron that winds up somewhere else or a photon winds up somewhere in the universe without actually crossing that space in a fashion that we would think of. Because again, if it's a particle, and Einstein argued this, by the way, this I have to disagree with Einstein's argument in this one. And man, I love that guy's thinking on it. I got to disagree with him on that one, but because he used that as the argument to say that photons were real particles. Say it's emitted here, it's theirs, it must be real in between. But that's an incomplete set of the data. The data does not say that if you take into account reflection effects. If you take into account the full ability of the wave to do all sorts of intermediate interactions that deposit momentum, leave a signature, have a history, and yet do not cross a specific location, double slit experiment being the most obvious, then you have to have something a little more complex. Other questions?
Yes, there's the second question from Jay. Could you please repeat with what you said on the cyclic cosmology?
On the conformal conform. See, I can't even remember
Yes.
it. Even after I just had it, I'm
That's
like,
fine. That's fine. You explain it
conformal
later.
cyclic cosmology, I think is
Yes.
Roger Penrose's acronym. So what was your question, Vijay?
Yeah, I just wanted to re-listen to what you said. That you explain it later. I'm good.
Okay.
Yeah.
And I see William Stiller posts a quote. There's a theory which states that if ever anyone discovers exactly what the universe is for and why it is here, it will instantly disappear and be replaced by something even more bizarre and inexplicable. There's another theory which states that there's been already happened. Douglas Adams.
Well, I can believe that. I live in the U.S., so I can believe that happened. My reality has been replaced by a bizarreness that I do not comprehend. There was a science fiction story, a lovely little science fiction story. I can't remember the name of it. I just reread it just a couple of weeks ago, in which I think it's like the 1 trillion names of God or something like that. So you got this. I think it was sort of a version of Buddhism, but it was an Eastern religion, and they had the monastery. Their whole purpose was to give every name of God. When they got the final name of the gods, everything would disappear. And the guys were helping them with a computer, and they were very happy. And the guy was driving off and watching suddenly the stars start disappearing. So it's just a delightful little story. It's can't remember one of the classic authors. Bill, do you remember who it was?
Yes, it was Arthur C. Clarke, and it was
Yeah.
a short story called The 9 Billion Names of God.
How many billion?
9
Nine.
billion,
Nine. Okay.
9 billion names of God.
He got very
And-
specific on the number. Yes.
Yeah, the Hindu prophecy was that when they can enumerate all 9 billion names of God, the universe was going to disappear. And so the guy was flying away in an aircraft with his friends, wondering if this was really going to happen. And it's very poetic. It says,
Yeah.
just overhead, he noticed that the stars were going out. So you get the feeling that there was some real substance to this prophecy.
Well, now, not there would be any cautionary tales for us nowadays with all the massive server farms and artificial intelligence,
Right.
and they were helping out in the technology, and they were going like, I'm sure it won't hurt anything. I'm sure I'm sure there's nothing going on with that, and of course it has that result. So kind of a cautionary tale about our interest in technology sometimes. It's funny because for those of you who follow me on LinkedIn, I am what we're doing now is not what I would call AI. It's a holographic database. It's a very poorly implemented holographic database. Holographic databases are really cool. They're interesting, but you don't want to present them as being AIs because they don't have they do these horrible just drifting things because it's a database. So, and simultaneously, I am still very much interested and participating in issues about what I would consider interesting AI research, low energy AI research. When you get a machine that's smart and only takes a watt of power, that's interesting. This brute force stuff is not interesting. I mean, people may have fun with it from a stock viewpoint, but by the way, I live in a city with more of those server farms than any city in the world, as far as I know. So there's one Raxpool Road, you can go down and you think you're in a sci-fi movie. It's bizarre because you get these giant, enormous boxes stuffed full of NVIDIA chips. And by the way, those chips don't last very long. And they have all of the safeguards have been taken off of them. Did you know that? I thought that was really cool. They took off all the safeguards, so they make errors all the time. So if you try to use some of these GPU chips for something with a precise calculation process, they will fail. And this was a prime number research team, which I encountered that very vividly. They simply couldn't use them because they had too high of an error rate. So,
Terry, to add to what you just said, it's remarkable that NVIDIA has become the world's first publicly held corporation that's worth over $5 trillion.
5 trillion.
And and then the other thing, and this is for the Luddites on the call, you can go look up what a Luddite is, and it's not it's not disrespectful at all. Sometimes I'm a Luddite myself, but what here's what bothers me. This thing, we got the cart before the horse, because now without proper planning, the Facebooks, the Googles, the Apples, the Microsofts of the world are sucking so much energy off the grid with their AI that the consumers are now feeling
Yes.
it. Our electric bills have gone up like 15 or 20% since August. With whether or not we're participating or not, we're participating with our limited financial resources because they're going to get their money for their AI, whether we're participating in AI or not. And I just find that morally wrong.
Oh, it's the strange thing about this is, and again, I've been active in the AI research community for long enough that I knew Jan LeCun and supported him back when nobody knew who he was. So that tells you how old I am. Also, I did a paper on reflexive. I got to find that thing. Reflexive intelligence is what's going on in most of these cases, where you fool yourself into you're the one being smart, and the machine fools you into thinking that it's being smart. And they use that technique on ELIZA, and it has not changed. Many of the cases where people are convinced that the machine is extremely clever, and I've seen it with security folks, Bill. I know that security folks are actually quite prone to this because they know their field so well. The mirror that the LLM reflects back at them is terrifying because they're actually seeing a dark image of themselves. And for good reason, they find that quite frightening. But these are mirror devices. That's why I need to find that paper. That paper was 1977, so that's how old I am. that's how long I've been interested in this issue, because I wrote a paper about it, generalizing the Turing machine for delocalized intelligence. That machine human hybrids. So it makes it an interesting structure with that. So yeah, so I think I might write a new article, the $9 trillion of NVIDIA, as opposed to the 9 billion names of and when they reach 9 trillion, what will happen to the universe? Will we all disappear? So we'll see what happens. Okay, other questions? We digress in interesting.
There, can I ask you a question, please?
Yes.
Oh, going back to one of your first slides, you talk about the Professor Roger Penrose theory of triple C about conformal cyclocosmic. When you talk about the dual universe, I was wondering, as the universe appears to be expanding, what is going to happen in terms of entropy when you reach the critical stage where the things start reversing, going back in terms, trying to meet the other universe? Yeah. Is entropy will reverse as well, or will keep increasing?
Yes, and this is Roger Penrose's idea more than mine. But in fact, I was very dubious about it, and I am still surprised that I kind of embraced his idea, because I was kind of like, really? I don't think protons work that way. But essentially, he says that when you reach a point where scaling no longer has meaning, you've reset entropy. You start over. And he has a good argument for it. He's saying essentially it's the structure that gives us the entropy. And if you reach a point where that structure suddenly no longer matters, scale no longer matters, and you still have that energy there, you still have something. I'm not sure if energy is the right word, but you still have that something that's there, because it's a dual energy, it's positive and negative energy, and it collapses. So yes, he has a full reset on entropy. That would be an interesting question to ask Roger Penrose, actually. I wish we used to have astrophysica meetings back during the COVID crisis, and he was a regular every week on those meetings. And I wish those were still going on. It would have been delightful to ask him exactly that question. It says, does this reset entropy? And I think his answer would have been yes.
Yeah.
And
thank you. And the other question, a bit fundamental, and which I still struggle with trying to understand it. I'm aware that people don't like to consider the space-time as a medium, but I still struggle very much with this concept of geometry X, Y, and Z and T as an abstract concept. Just I wonder that it might have even Einstein might have thought that the space-time might have a physical
Implementation.
Identity, is not just an abstraction
Right.
of geometry. And then if that is physical, then it might have some kind of medium, whether we want to call it medium or not medium in terms of the way we describe matter, but in a different sense, that is a different kind of media with properties. And if it has properties, then if something is missing in terms of ontology of general relativity.
Yeah.
And I think this is critical, that we may have to understand what this medium, whether we want to call it medium or not, in order to develop a unified theory. What do you think about this?
Well, if you look back on the slide where I talked about an aeroboic field, it has a kind of a donut shaped structure, and then we're in the E positive component of the field. What you just asked and what I'm kind of suggesting with that are not that different, because that is the higher level structure that is imposing on matter and energy, and in doing so, creating this multi-level structure of spacetime. Again, I'm very reluctant to talk about a single spacetime. We absolutely have spacetimes that overlap with each other. When you have a train going by, it has one set of coordinates and measurements, but yours don't disappear. It is embedded in yours, and this is something I think that people try to get too fascinated by the emergence of the new one. They forget that it's embedding. It's not complete erasure. And it's easy to, if you work too much with the light, you can confuse yourself and forget that, yeah, it also can be recorded, and the recordings are very real. So I'm reluctant in that, but within that framework, the idea of these multi-scale hierarchies of space-time definitions would be driven by that aeroboic field, and that would be part of the quantization on it. And that's not a complete abstraction either, because as I mentioned also in that slide, if this aeroboic field exists, it's necessarily being evidenced in our universe as the Higgs field. That there's a connection between those two. You can't separate them. So the Higgs field, it would be our local interpretation, subject to some vagueness about how you define direction of time. That would be our vision into this aeroboic field, and I would agree that absolutely would have some difference. Comment on Einstein. Einstein, there's two Einsteins. There's Einstein pre-1911, and there's Einstein post-1911 after Minkowski died, unfortunately, of appendicitis very abruptly, shortly after Einstein had insulted him pointedly, repeatedly. So this was one of the strangest incidents in history. But Einstein had just called him chalk for brains like a few weeks before or something before he died of appendicitis. And he was pretty blunt. He said, yeah, okay, some people have chalk for brains, and then off he goes. We hear the milder versions of Einstein. Einstein did not like Minkowski's structure, his fabric at all. But after 1911, Minkowski, because Einstein was not a cruel person, he felt bad about that. I really think he did. And he embraced Minkowski's framework, which he did not understand very well even then. He had difficulties. And the contrast between these two Einsteins is stark, because Einstein pre-1911 was absolutely 100% clocks and rulers. He was hyper materialistic in how he did it for exactly the same reasons I was complaining about during this. If you don't have a clock, you don't have a ruler, you can't measure it. So what are you talking about? And that was Einstein before 1911. He was adamant on these issues about, you got to be able to measure it. And then after 1911, he fully embraced Minkowski and eventually went to 100% space-time fabric. So the contrast is just amazing between these two personalities, these two versions of Einstein. And there was a trigger event. It wasn't just an accident that it happened. The continuum idea, and again, having space-time as created by matter does not get rid of the power of the general relativistic space-time manipulation model at all. It just says that the origin of it is somewhat different, and also that it has more structure. And the latter part, I think, is the most fascinating part, because if you have the structure of general relativity just implemented in a different way, And you have to A, acknowledge that matter is part of it, and B, acknowledge that it's hierarchical. This does not remove from general relativity, it adds to it. It says that in places of space where there's very little matter, you have to take that into account. It says that in places where you have multiple different definitions of space and time operating simultaneously, you have to take that into account. So I think there's some rich opportunity there for looking at these issues and saying, where does this go? I think some intriguing possibilities there.
Yeah, thank you. My last question, please, is about time again. I get confused about these issues of time because I'm trying to understand time perhaps in a very simplistic way as as a rate of change of physical entity. If that's the case, then it should be a dual time, that we live in a dual time, in a pre-geometry time, which is a kind of a time with no present and no past, no future, the pre-geometry, and then the post-geometry as a time which has got a beginning, has got a beginning, and perhaps will have an end. So what are your thoughts on this idea of dual time?
Okay. By the way, this is Catano. How do you pronounce your first name, Catano?
It's Caetano.
Catano Peng. Okay.
Yes.
One of the suggestions I would make on that is this differentiation between change in separation and structured geometric time. And I think the state machine models, and again, these are not just ordinary state machines. Ordinary state machines we use exist in space and time. These state machines create space and time. They create their own separation. But if you use a state machine model, suddenly it becomes a lot easier to talk about the emergence of structured time and space as organized sets of operators. They have certain very specific cooperative relationships with each other. And that allows you to have a concept of change as defined by a state machine, which is not necessarily the nicely organized geometric time that we think of, but from that disorganized version of change that still follows formal rules, you can get coordinated emergences of things in which over a large group of particles, they suddenly say like, oh, I'm this far away from you and you're this far away from me, and we're going to stick with that, unless you're a photon, which everything goes out the window again. But it at least gives the illusion, especially for fermions, that this is really intransient. It stabilizes. And he goes like, oh, within the state machine, if you follow a certain set of rules and everybody will cooperate, say, oh, put their hands together and say, hey, we're going to do this, then suddenly you have your geometric emergences. But again, that emergence process has to be hierarchical. We talked about the CCC model. One of the things I don't remember if I had that slide in there or not, but the idea is that you can actually have cycles in which the complexity builds with each cycle. That you start out and originally there may have been nothing but electrons and positrons. But then things got a little squirrely and some other things popped in. And the context is just like in real life. Context creates complexity. No context, no complexity, it's very boring. But if you have these cyclic universes in which each iteration gets a little bit fancier, gets a little bit stranger in some ways, has a little more context, then suddenly you can get universes where structure can emerge on a much larger scale. Space is just a fantastic invention, a device, emergence, whatever you want to call it. But instead of thinking of space as just a given, think of it as saying, how did the universe come up with this? Because it's just such an amazing idea that particles can have separation from each other. Why, we're so used to it, we don't think otherwise. But it's a remarkable concept that we have separation. So like, what was the expression? So every space is so everything doesn't have the same. Time is so everything doesn't happen at the same time. Space so everything doesn't occupy the same point. And wow, you can have more nebulous forms of change, especially if they're cyclic and emergent, that I think can lead to that. So I just think there's some, if we abandon certain things as being necessarily fundamental, we actually have an chance to explore them better and understand them better on what's going on. And I think structural space-time. Yeah, Bill?
Yeah, thank you. Thanks so much.
Okay.
Sure.
I have a question, if it's okay.
Oh,
Oh,
yes, Katina, yes. I noticed you post some questions.
yes. So I'm not as smart as you guys. I'm kind of a novice, but it fascinates me. I've been reading the declassified documents on the CIA website about remote viewers like Ingo Swann, a few who are still alive today, like Lynn Buchanan and Joe Monteagle. And supposedly they were able to observe the reason why the CIA had them, they were able to observe outside of our time, outside of our frame of reference. I wasn't there. I don't know how true it is, but the CIA thought highly of them and paid them. So it must be something to it. That's what I'm thinking. If that is the case, do you think there will ever be an attempt, by physics, people who make decisions on what's considered normal or not? Do you think there will ever be an attempt to explain that, like quantum backflow? I guess that's what you would call it if you're able to observe information from a reference prior to where we're at right now. Does that make sense? I'm not scientific like you guys.
Well, the first comment I make, I've never heard of any of those names you mentioned. And I do know a lot of the research community. I live in the DC area, so I know a lot of people. So none of those names are familiar. When I worked at the Office of Secretary of Defense, we were, in movies, they occasionally have the place where people send unusual ideas to the Department of Defense. And then there's somebody there looks at them, and that we actually were that place. We got some very interesting ideas sometimes. So in the very fact though that I worked in that place and that we actually did see some of these things, we had some delightful stories about some of that. I again have not heard of those, and I've heard some really unusual ideas. So I don't know what that would be about. So I'm trying to interpret your question. Is it some kind of surveillance question about,
I'll simplify it. But first, let me just say, just if you're curious, if you go to the CIA websites, anybody can go there, CIA.gov, right?
Yeah.
And you put a name, Ingo Swann, INGO Swann. He was a remote viewer, or Lynn Buchanan. He's alive today, and Joe Monteagle. So, I mean, these are literally on the CIA websites for FOIA, a Freedom of Information Act. If you go to that section, it's declassified. Anybody can read it.
But
So
what
my
did they
question
do?
for you, remote viewing. So remote viewing
Is a kind of Terry, is a kind of telepathy. Is a kind of telepathy. Someone far away can guess what's going on somewhere else. It's
Thank
kind
you.
of telepathy.
To make my question simpler, I'm like, have you ever heard of quantum backflow? I mean, I've read a lot of research papers on that. Have you ever read about quantum backflow?
No, never. It's the first time I've heard the term. It would be incumbent on both research community and on the CIA, and they have their own research groups. There's multiple different research groups in the Department of Defense, which is where I worked. There's some other name for it these days. It is incumbent upon them to research areas where it's extremely unlikely to be true. I mean, they literally was sitting there and said, I don't think that's going to work, ever. Warp flight is an example. NASA has had not massive, but had large research projects in warp flight. So I would describe them as not doing due diligence if they did not look into the possibility of remote telepathy as a real possibility. So the fact that I haven't heard these people doesn't mean that they haven't been employed. And yeah, they've looked into it, but they should, because Russia in particular has done a lot more research in areas like that than the U.S. has. I think generally that has not been one in that. I am not familiar with any of those components of research. I am very much familiar with some of the cold fusion research, and I've seen some of the things in that, and talked to project leaders who were working on that. You know, those are examples of those kind of things. But I never encountered that group, so I don't have any personal information about that. If they had succeeded, here's another thing that's worth keeping in account. I have never seen a technology that was extremely useful that didn't leak. I can even give it, well, this wasn't a leak, this was declassified. You've seen these LiDAR maps of geography in which all of a sudden you can see tombs and you can see roads and you can see things that no one could ever see before. That was originally classified. And I remember the first time I encountered it, I said, oh my gosh, they can do that? They can do through the trees, they can see all that. And I remember thinking, I said, that's impressive. But technologies like that don't stay classified. For one thing, technologies usually are not the points that they classify, except for things like nuclear, but rather the specifics of the situation. So if they had succeeded in doing remote telepathic, I would incline to think that that could be something that would have gotten out with that. But again, you know, Russia's the one who's researched the idea of controlling people remotely. They've done a lot of research on that. So they're the I would hope that folks on other countries would also look into it. Some of that.
I just found it interesting, but like I said, anybody can read it. It's on the CIA website under their FOIA section. And Ingo Swann is a very interesting person. He's no longer here, but just in case you ever want to read up on it. But I've read a lot of research papers on quantum backflow, but I guess you're not familiar with that.
Never, and that's a little surprising because I've seen a lot of issues, a lot of discussions about different philosophies of quantum mechanics. I have a very hard time even understanding from the wording what that would mean. I don't know what backflow would mean in the case of quantum mechanics. Now,
I guess it would be like sending wave packets or quanta of information to, you know, different time frames of reference.
Yeah. I am guilty myself of putting out an article that was prominently put up for a while on a Russian website about backwards propagation of causality, which is that when you have when you do this quantum encryption thing, it was on the topic of quantum encryption, and I had made the statement that what happens is whichever side sees something first, it is as if you went back and changed the original cause, that you actually set it and made it classical. And then that flowed back upwards through time. So that was, I think, in 2002. I don't remember, but
what was the name of the paper, if you don't mind?
Oh, I'll send a link to Helen. She can send it on to you. I still have, actually on my website, I think I fortunately made a copy of the Russian discussion of it because they took it down later when things got tense between that. But they had, back when they were actually doing more typical commercial things, they had it up there. Yeah, so the idea is that and I would say that assertion, when you're talking about something quantum, it is as if that event has not yet been settled. It has not been determined. And that seems to be mathematically true for all quantum phenomena. You know, so again, that photon example I gave earlier, it seems like it's going out to the entire universe. You can even measure it going out to the entire universe. But until you actually get an energy event where it whacks down, then all of a sudden it looks different. Then you have a definite path. You can describe this path that went through everything as if that path suddenly came into existence.
That's basically what Richard Feynman said on one of his lectures that I watched on YouTube. He said the laws of physics doesn't disqualify that from, no matter how small the possibility. And he actually did have a number for it. It was like some weird number that I can't even fathom. But he said it doesn't rule out that happening.
And that was his whole insight. Richard Feynman's whole insight was that you should look at all the possibilities. And if you ever read his book QED, if there's a book by Feynman called QED, I would highly recommend it. He wrote
Okay.
it without mathematics. In fact, he had to cut some footnotes. He was doing for an English professor, friend of his. And he talks about this issue about, for instance, he says at one point in the book, he says, could a photon go in loop-de-loops in a little circle in this way and this way and that way? And I said, sure, because what happens is the probability of that becomes extremely slim, but it never fully disappears. So he has this marvelous description of how to look at all those issues, and QED talks about that beautifully. I think my next talk is to talk about that. Yeah. So my next talk I'll be addressing some of those issues because
Thank you so much. I
it's a
look forward to
beautiful.
getting that link.
Okay. Good
Just
luck.
comment there to Katina. You're not the only person who heard about this story.
Thank you, because I'm not smart
Several
like you
years
guys.
ago,
Thank you.
I've heard about this remote viewing, not only for USA, but also from USSR, from Soviet Union.
Yeah.
Many years ago, the Russians did similar kind of studies on remote viewing. Now, whether they were been successful or not, that's the question mark.
Yeah.
Yeah, if Russia could actually do that successfully, they could make whole groups of people do really stupid things.
Well,
Can't
yeah.
imagine that.
I will be looking forward to your next
That's a scary thought,
presentation.
actually. So QED, somebody put that in there. Yes, yeah. Oh, great little book. It really is. It's just a lot of fun because he does a better job of conveying quantum weirdness and how you just have to accept the fact that that's how it works better than anyone I've ever seen on that. And one of Feynman's hallmarks in comparison to unfortunately too many people is if he couldn't explain it simply, he felt he didn't understand it well. And his goal was always to explain it to his dad, who was a tailor. And I love that about Feynman because he will get into extraordinary detail, but his goal was always the same. It's just how can I
Yeah.
explain this really simply?
That's why, as a novice, I became really entrenched in quantum mechanics because I was looking at his videos on YouTube, and suddenly I realized I was understanding what he was talking about. And I was like, "Wow,
Because yes,
I may not be the smartest person, but I'm understanding what he's saying."
Feynman was adamant. He would say repeatedly, he said, I'm just an average guy who just has a really strong interest in this. I think most people around him wouldn't quite agree with that, but he was sincere about that. He said, yeah, because he would spend hours every day just poking at some problem saying, I don't understand this. And so many, it's so tempting sometimes to rest on our laurels and say, well, I understand this really well, and then not do anything. And Feynman was such a beautiful representation of the opposite approach and saying, I mean, later in life, he was disappointed himself. He said, I never explained the mass of an electron. And he found it very disappointing. He said, I never figured it out. And that's just a representation of a truly inquisitive mind when you think of things that way and say, like, I don't know. I don't know how that works. And let me see if I can find out more. So good luck on that. And like I say, recommend the book. I think you'll like it.
Yeah, Katrina, that was I just look now. A physicist called Russell Targ, and Harold Pathoff at Stanford Research Institute, SRI, in 1970s, built on ideas from Ingo Swain, who refined the training methods. CIA Stargate project.
Yes.
That's it. You can find that on Wikipedia.
Oh yes, but I would I would encourage everybody, just go to the CIA website and just go to the FOIA, because people will think it's hocus pocus if you don't literally read it from the CIA website. So Project Stargate, thank you. That is the name of it. Thank you.
And again, if the security agencies do not investigate issues like that, and this I think surprises people, they're not doing their job. The fact that something is incredibly low probability and everybody thinks it's not true, some cases exactly why you should at least look into it. NASA, bless their hearts, we got more, when I was working at that one place, we got more unusual items out of, at least in one case, my reaction was, whoever you are at NASA, you're being conned. This guy's not legit because he's contradicting himself. And you go like, be very careful in some of that. But there's also extremely interesting, sincere ones that go down. But it is incumbent upon different agencies to explore unusual possibilities. Going back to what I was talking about the model, remember I keep talking about a state machine model. Here's the flip side of that. If you're interested in topics like that, why is an electron here exactly like an electron on the other side of the universe? If they were just copies of each other, then it doesn't work that way. They would mutate, they would change, they would alter over time. In some sense, and Wheeler was the first one to say something like this and inspired Feynman to get his idea that got his Nobel Prize. Wheeler suggested that maybe there's only one electron, goes back and forth in time. And Feynman thought that was ridiculous, but then he said, but if I constrain it, what can I do? And got his Nobel Prize for it. So there's a connectedness to the universe that we do not understand. And this, again, is why I think going with a state machine model in which you start and saying, oh, there's a spot where the idea of location doesn't exist. Ooh, think about that. If you start with the premise that the idea of location does not exist and the location has to be an emergent property, that's a very different worldview from what we usually think of. So, and yet you look at simple examples like why are all particles exactly the same? And one way or the other, you have to take that into account as part of the underlying mechanism that produces all these rules. So there's plenty of room for exploration of ideas we don't understand yet. Any other questions, anybody? Bill, did you have a?
Sure. I wanted to share something. This is very personal, but if you live long enough, this will become more and more real to you, and you'll remember what I'm sharing here. I just turned 70 back in October, and so there was a strange thing that happened, and you can go look this up on the web. It's called AFib. My heart went into AFib for the second time since 2023. And the reason I'm sharing this is, time is this paradox. We all want more of it, but the more time you get in your life, sooner or later you won't get any more time and you'll be gone. So anyway, I just wanted to share that on Monday, January 13th, I had to go get a procedure done called ablation, heart ablation. And so this is at nearby University of Illinois Health Center. And I'm in my 70s now. And the guys that did this are in their early to mid 30s. And they put two probes up through femoral veins in my groin and drove these probes right up to my heart. So the long and short of it is they spent 3 hours, thanks to technology, they spent 3 hours, 180 minutes inside my heart. And it's Saturday, January 16th, and I'm here to talk about it. It's kind of a big deal. It's kind of a miracle. I've got a positive outlook on life. I hope to live another 20 years or so because I've got a wonderful wife. But I had two guys in their 30s probing around in my heart for 3 hours on Tuesday. And I think that's a bit of a modern technical miracle. And I wanted to share it with you guys. I came out with flying colors. Everybody was super nice. They said I did very well. But it's 2026 and here we are. And I'm not looking for sympathy or anything like this. I'm just sharing there's a whole lot of physics that was going on that was helping save my life. And while they were inside my heart, they were doing these electrical charges that were kind of like burning off areas of my heart that weren't functioning properly and helping strengthen my heart through this heart ablation procedure. So I wanted to share that personal example that what I went through 3 days ago. It's kind of a big deal in my life.
Bill, congratulations on that. And it is amazing what they can do now with minimally invasive surgery. The fact that you're doing great, you're here. I've heard about those cells. You can get little clumps of cells that they start throwing off the rhythm of the heart.
Exactly.
So they're ablation, getting rid of those cells makes sense. So yeah, just some of the things we can do now are just astonishing. If there was a recent Veritasium video on what they do to make chips, advanced chips, can you imagine dropping tiny little drops of liquid tin in a continuous stream and hitting them with a laser not once, not twice, but like 3 times in order to generate the ultraviolet rays they needed to do that? I look at that machine, I go like, I cannot believe that humans were able to build this thing and make it work that reliably. So the technology is capable of incredible things. Medical domains, like what you mentioned there, there's very cool things in our future if we don't mess everything up in some way. So I very glad to hear that went well for you. Anybody else?
Yes, I saw Robert Becker.
Sorry, if I can comment again, something also I think might be interesting to Terry and Bill as well. Is first of all to Bill there, it's very inspiring, your story, and gives us hope in science and technology in solving the humanity problems. Going back to physics, I've been warned that I'm not a physicist, and I don't want to pretend to be a physicist, but sometimes I think more on philosophy side than in physics. And I've been wondering recently about the self-similarity principles. And based on the self-similarity principle, I start imagining a mechanical universe. And the similarity principle says basically we have similar principles, underlying principle from micro scales to macro scales, to different scales. It means that certain phenomena that we observe at lower level, they are replicated at a higher level, not exactly in a structural manner, but in terms of patterns. And if that is true, then the question of space-time, if you look at space-time as a medium, then you start thinking like some other theories like the superfluid dynamics. And you can start thinking that what we perceive as GR gravitational waves and electromagnetic waves, they may be just same phenomena of space-time in terms of, I'm thinking in terms of mechanically, as resonance of the medium, both. Although the electromagnetic are considered as a kind of vibrations, the are considered both of them, both gravitational as and electromagnetic as resonance, but different modes with same frequency, which is speed of light. Now, how could they have different modes with same frequency exactly? It means that the space itself may have a multi-moduli, multi-stiffness, and multi-density. If that's correct, then it may be possibly to unify these two different phenomena. And also, if you think mechanically also, you can think about piezoelectrics, that the electrical mechanical interaction, that the electromagnetic and gravity, they may interact. So I see that it might be possible in the future that someone may develop this kind of ideas, that it may, based on this self-similarity, that they could find a solution to the question of unifying the theory of physics. So I wonder what you think about those ideas, like Terry.
Cateno, two things real quick. By the way, Helen, I think somebody else was going to ask a question. Is that correct? Or
Yes, Robert Baker.
okay, I'll answer this real quick and then get back to that. Two things. Self-similarity and quantum mechanics have a very close relationship. And this fools people sometimes because you think self-similarity is, it's just self-similarity. It's repetition. But you do repetition at the quantum level, like a repetition of a crystal structure, and all of a sudden it has quantum properties that are completely impossible otherwise. You get resonances, you get reflections, you get human scale quantum phenomena by repetition. And so repetition is an interesting. It's part of our universe somewhere. You like I say in the quantum level, you can't even distinguish between protons. The context is the only thing that tells one proton from another proton, or one particle from another particle. In terms of the unified, have you ever looked at Einstein's unified field theories?
I look very briefly.
Yeah, because he of course he was trying to do that. He never succeeded at, but he tried. Oh gosh, for a long time, and you could get into an interesting discussion about where he might have gotten himself stuck because he had trouble making progress with it. But he certainly was interested in just that idea that there could be some kind of relationship. Yeah, I'll mention one other repetition issue, which because I have locked into this idea, and once you get into it, it's really hard to it's hard to get out of it, is that every instance of matter is creating its own instance of space-time. And so if you have a well-defined piece of matter floating in space, it necessarily has its own little local definition of space-time. It's also embedded in other ones. So there's nothing, conflicting about that you have the other ones. But for instance, when I say local instance of space-time, think about a centrifugally rotating system. What is it rotating in comparison to? And people have this Mach's principle. This is driven. Einstein was absolutely fascinated by this issue about what is rotation relative to the entire universe. Speed of light violation. So be careful about that. If you have the idea that the matter has its own definition of space-time and rotation is simply one of the parameters to that definition, you get a much easier explanation for some of those phenomena like that. And by the way, rotation also starts to look a little bit like momentum space. You have some of the same asymmetric centralized characteristics of momentum space. So I think we have interesting games going on different, almost like space alchemy, that you create different instances of these spaces. And it just gives you a different way of looking at that. And of course, saying that rotation is intrinsic is particularly, for some reason, it's particularly heretical in Britain. I don't know why, some kind of historical thing about that. But even suggesting that centrifugal forces are in any way real, it just gets this really strong reaction. And but the rotation is relative to whatever you rotate it against. You take two pieces of matter, they rotate relative to each other, but then they can separate to an indefinite distance. The easiest explanation is they have their own instances of space-time, and that space-time is more complicated than just location. It also can have things like rotation. So, Helen, what was the other question? Someone?
Before you move on, it's a book called Swinging of the Wild Pendulum with I think his name is Ishtar Bentov. He discusses how matter is fractal, and it has like resemblances of other fractals within the world where you can see those different iterations. I
Sure.
don't know if you ever
Sure.
heard of the book, The Swinging of the Wild Pendulum.
Well, and one reason why I mentioned that about hierarchical spacetimes is hierarchical spacetime instances embedded in each other, not excluding each other, but embedded in each other, is a fractal structure, an extremely fractal structure. In fact, it goes all the way down to the particle level because particles have spin. And if spin is a property of spacetime, it means every particle has its own instance of spacetime that is part of its structure. So I very much like the idea of fractal structuring of spacetime with self-similarity across those levels, because I think that's a big part of what's going on. But I think it's being mediated by this concept that we can construct different instances of what we call time and what we call space with different sets of properties in some cases. So a fermion does not have the same space-time properties. Oh boy, does it ever, as a boson. Fermions technically shouldn't exist in our universe because they rotate in a way that violates our concepts of XYZ space. But I think that's exactly why they do persist in the universe, is because they do violate that. There's a conflict of space definitions that is extremely important for persistence. So yeah, interesting stuff. But I love the idea of fractal universes. I think that's good. Swinging of the pendulum. Yes, pendulums get chaotic after a point.
And Robin has asked question, how many levels are there to the space-time emergency hierarchy? Finite or infinite? If the latter, how can that reconcile with the rejection of infinite meal?
Finite, but unbelievably large. The universe, when I said that the universe has finite data capacity, that data capacity is just unbelievable. The data capacity just of photons in free space, which people tend to forget about. Free space is not empty. It's got photons in it. The photons are essentially a memory device. And do you ever think of that way? Empty space is a memory device. Not only is it a memory device, it is a memory device with unbelievable amount of data in it. And this is why I think when people say that a spaceship's going through space, free space all by itself, no, it's not. It's embedded in that entire matrix of all these photons. So there's just some interesting issues about, I think I lost the bubble. The question again was, I drifted too much.
My point was that you had started, in fact, it's ironic that, or maybe not coincidence that you ended up on exactly the point I was asking about a long time ago, which was just what Helen just read off. You mentioned emergent space-time as being hierarchical. So my
Right.
question was, how many levels of the hierarchy do you see?
There are many, many levels, and they are very much finite. But it's just extremely large. And the levels are, in fact, for instance, planets are one level of the hierarchy because you have your own definitions of space-time at the planetary gravitational level. So you have multiple levels of hierarchy there. Binding and matter creates instances of hierarchy. When things bind together, they are forced to share a common definition of space and time. And again, and I would say the fractal starts at your supergalactic scale, your galactic walls. Something's going on there we don't understand well. Then it goes all the way down literally to the particles, because if a particle has spin, it is part of that hierarchy. And I think that's actually where it gets. And it's at that level, it's not just a hierarchy, it's also a network, because they're also sharing something in a way that we don't understand. So extremely large, but the levels correspond to more what we would usually think of in our power law universe. I think it'd be interesting to see if that's one of the reasons why we have power laws, is because these hierarchies are enforcing those power laws. They're actually creating these power law relationships in that.
Okay.
I've got my
But
hand
it
up.
is,
How
but
do
it
I?
is,
How do I keep?
there is a finite number of them. All right. All right. From the small, so we don't have to worry about an infinity of hierarchical levels.
No, because it stops. Even in the Planck foam model, Wheeler's Planck foam model, it stops because eventually you get down to, that was his way of resolving the infinities, was eventually space and time become, he had a name for them, eons. It's some kind of unusual name for the particles. So he would terminate at that level, and that's been kind of accepted as gospel sense. And all I'm suggesting is no, it terminates a lot higher than that. It terminates roughly at what we think of as particles. And then those particles can do things, but really there's not much, there's no detail below that level. They have those sets of properties, and that's it. So not an infinite hierarchy. It's a very, very large one, but all the pieces are familiar to us. And I think for good reason, because they help compose a universe that has enough structure and time and repeatable definitions that we can make use of it.
Okay, thank you. And by the way, Bill, congratulations on your recovery from that surgery so rapidly.
Yes.
That was most impressive. There are at least three of us here who are the same age, very closely, you, me, and Terry. and hopefully we'll all be able to enjoy these things for many more years to come. I've had my own shortcuts with mortality in the last few years, and glad you got through that.
And
Thank you.
yes, thank you. And I'm coming up on 71 myself, just very shortly here. So been there, and yes, modern technology is marvelous. I've had my own experiences. I'm a little surprised I'm still here. Let's put it that way.
Well,
Not
let
only
me
here,
know
but
when that happens, and I'll sing you an operatic happy birthday on this on
okay.
these Orion X's here.
Now, when you say when that happens, you meant my birthday, not my demise, right? Because I can't send you any notification on
Yes,
that. I
well,
mean,
I don't know. With your theories, I'm not so sure about that. There might be a way of doing that, but
who knows? Who knows what's going on? So, yeah, having near-death experiences can mellow you out in many ways or make you more nervous. But boy, in my case, it sure mellowed me out. I'm my lack of worry about that is impresses me sometimes and surprises me. But um, I'm good with the universe these days. So, any other questions or inquiries?
I got a good feedback from George Sipperland. Terry has done a beautiful exposition of time in the geometry of relativity. In quantum mechanics, time is due to energy. That strikes me as the essential incompatibility between the two theories, in that energy is a conserved quantity.
Yes. Yeah. The momentum space I've always been baffled by. In momentum space, you have things that move replaces location, and you have time, you have energy that's static replaces time. Think about that. That's really odd. That's very, very odd because in location space, the other way around, you have space that just kind of stays there, and you have the time that's continually moving. I do not think that's a coincidence. I think that is part of this deeper relationship and really a literal symmetry break between the two. They sort of like negotiated one day and said, somewhere out there in Octonian space, and said, you know what, this feels uncomfortable. I think I'm going to collapse now. And that's the point where you get this what we call a Big Bang, and it goes out this way, and momentum space gets all compartmentalized into little things called particles and all our other stuff. But I just think there's some fascinating symmetry issues that are going to pop up eventually about how some of this works. Yeah, it's intriguing. Energy versus time. It's just not obvious. Not obvious. Anyone else?
So far, I haven't seen any question. And George said, once again, thank you for a wonderful presentation discussion.
Thank you, everybody, for the questions. I always enjoy that. A lot of good participation and a lot of fun.
Yes, and your next one is February 21st.
And Greg, remind me, that is the light one in which I'm simply going to go over Feynman's QED and talk about some of the marvelous little figures and things he gets into. Does that sound right, Helen?
Yes.
Do you remember? Yes. Okay. So that one will be a nice, I think a nice lightweight one, but I just love that little book. And it's one of the most inspiring books, only book I ever used to give out copies of. I would give out copies to people just to let them see that. So we'll cover that next time.
Sure. And see you next week, January 24th with Ishan
We got several talks coming up. These should be good ones. They got some good stuff coming up.
Yes. And goodbye, everybody.
Okay. Goodbye, everyone. Have a great January.